Hello everyone. This is my second video. In this video, I wanna introduce the method of linear regression. Um, let me use the same example I used on Monday. Here we have bivariate data. The X are the heart rates um, before the people who took exercise, and the Y value are the heart rate after taking exercise. Okay. Um, so right now we have this scatter plot of this data, and our goal is to find a straight line that will fit this data. Okay, so here we're gonna use the knowledge about a linear equation. What does the equation of a straight line look like? The equation of a straight line. Okay, equation of a straight line. Okay. Um, In algebra, we have learned that there are more than one way we can define an equation of a straight line. But here we only use one equation, one type of equation, that is called the slope and intercept form. Okay, so a slope intercept form has an equation looks like this: y equals mx plus b, where both m and b are some real numbers. Okay, some real numbers. Okay, the m will tell us the slope of the straight line, and b will tell us the y-intercept at what point the straight line will pass the y-axis. So that is called the y-intercept. Okay. So for example, if we have an equation looks like this, and so we can tell that from this equation we can tell that the slope is 1.42, and the y intercept is negative 17.84. Okay. Yeah. Okay. So after I review the linear equation, now let's think about what would be a good line we can use to fit these points. Okay. So here in the decimals, I have already input these points. So I just made three equations, three straight lines. Okay, one and two and three. Okay, so how can we? Well, they all looks good, right? They all looks good. But is there a way we can decide which one is the best, I mean, among these three lines, right? Because they all pass majority of the points, right? Yeah, so how can we figure this out? Is there a way to make the decision, to help us to make the decision? Yes, we will use something called residue. So residue is you can think residue is an error. Is what kind of error? Is the error, it's the difference between the observed data. So what the observed data is the real data, right? This is X, this is Y. So all these are the observed data. So they are the actual data, or the actual data. Okay. And you use the actual data to minus the predictor data. So where the predicted data is from? The predict data is from the equation. The predict data is from the equation. For example, let me use this. Suppose this is the equation I choose. Okay, this is the equation I choose. So uh, and when we write down the equation, um, we for y we like to put a hat in front of the y, because just to show this is not the actual y, this is a predictor y. Okay, so suppose I decide to use this equation to fit this point, the 1.42 x minus 17.48. Okay, sorry, 84. So for the when x is 86, right? When x is 86, the predict the predicted value, the predicted y value when for 86 gonna be 1.42 and times 86 and minus 17.84. Okay, and that is equal to okay, I didn't do here. Okay, so that is equal to, let me go here, 1.42 times 86 minus 17.84. Right? Okay, so that's a 104.28. 104.28. Okay, so this value is the predicted data. Okay, and to find the residue or the error, we use this um, here. We use the actual data to minus this predicted value. Okay, so the actual data for 86, that's 98, right? You see here, it's 98. 98 is the actual data. So add 98 minus this predict value. Okay. And this result, um, negative 41.96, negative 41.96 is the residue for the first data, right? For our first data. Okay. Yeah. So that's how to define the residue. Okay. Now then, how can we use how do we use the residue to help us to make the decision? We find the residues of all this data. Okay, so we're gonna have a bunch of 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're gonna have 9 residues here, and each residue we square it. We square it. So we square this residue. So we're gonna have a 9 square. Okay, and we add these 9 squares, and the sum um and then we compare this sum with um we compare this sum with another equations. Say if I use the second equation, if I use the second equation and find the residue and then find the sum, and then I can compare these two, and the one with the small sum will be better. Okay, the one with the small sum will be better. Um, so example here. So here we have this 5 data. So 1, 2, 3, 4, 5, right? And suppose I decide to use suppose I want to use this equation, and here this is the residue, right? The difference between the y value of this point and this point. That's the residue. Okay, and when I square this number, that is like I'm finding the area of this square, right? Because when I square this, it's like I multiply this 9. I multiply this number by itself. So that is the same thing as a square. Sorry, same thing as the area of this square. So I have one square and second square, third square, fourth, and fifth. Okay. So by adding them together, I will get a number, right? Then I can compare that with a different equation. Say, for example, suppose I give like this equation. Well, now you can say if I decide to use this 9, if this is my second 9, and obviously the first one will be much better than the second one because the second one will have a large error, right? Yeah. But in practice, we don't have to compare them one by one. In practice, there is a way we can figure out, we can determine the best straight line, the best straight line. And that line is given by this formula, okay? Its slope is, we call the slope as B1. We use B1 to indicate the slope and the B0 to indicate the y-intercept, okay? And the slope is determined by these values. Now, if you still remember, the R is the correlation coefficient, right? Like in my last video, correlation coefficient, that's the R. Okay. And Sx and Sy, they are the sample standard deviation. Okay, the sample standard deviation. So Sx is a sample standard deviation for X, and Sy is a sample standard deviation for Y. And we found the ratio of these two sample standard deviation, and then multiply by correlation coefficient R. We can find the slope. And the intercept is given by, so Y bar is the sample mean of Y, and X bar is the sample mean of X. Okay. And we multiply the sample mean of X by the B1 and subtract it from the sample mean of Y. Then we can find the B0. And that will be the best line. In other words, this line will give us the least square. Okay, this line will give us so using, in other words, using this kind of line, the sum of all this square will be the minimum. Okay, the sum of these squares will be the minimum. Okay. All right. So now let me use this data and use the Google Sheet to show you this. Okay. So here I have already put the data and enter the data into the Google Sheet. And remember the correlation coefficient, how do we find it? We use this function CORREL, right? And then you enter the X value, where you save the X value, where you save the Y value, okay? And for the sample standard deviation, remember we use this function, right? And because say here standard, right? Remember there are two standard deviation. Remember to use the second one, the one with the dot S, because that's the standard deviation for sample, and this is the standard deviation for population. Yeah. We don't want to use the standard deviation for population. Yeah. And a second thing you want to be careful is there are two standard deviations, right? One is of X. So when I use this one, or when I find this one, I'm using the data of X, right, from A2 to A10. And when I'm looking for the standard deviation of Y, I'm using the data, say, from B2 to B10. Okay. And same thing for for the mean, right? So you make sure you use the right data, right? For y, I'm using this data, okay? Okay, so after I found these values, though, so I can find the b1, right? I found a b1. So using the um, sy divided by sx and multiply by r. So here, see, I'm using the sy 21.63 and divide by yeah, so sy 21.63 divided by sx 13.017 and times the correlation coefficient 0.406, and that will be the B1. So it's around to here 0.67, 0.6747. Okay, and then we find the B0. So B0, I'm using the sample mean of y 89.33 minus this B1 0.6747 and multiply by the sample mean of x, which is where that is 71.778. Okay, and the result is around to here 40.9. Yeah, 40.9. So this linear regression equation is 0.6747x plus 40.9. Yeah, yeah, yeah. In the homework, this is called a linear model. So if you see the question asks you to find the linear model, this is the thing you want to find. Okay. Okay. So now let me put this equation into decimals. So y equals 0.6747. Yeah. So it turns out the best line that will fit these points gonna be this one. Let me change the color. So what choice do I have? Okay, let me use orange. Okay. Yeah. So it turns out the best line is this orange line. Now you may wonder why, because the others that seems to be very close to this point. That's because here we have a weird point over here, right? So this weird point, because it's far away from these points, it's far away from the rest of the points. So if we use if we use a straight line like this, that will increase the error. So therefore, the best line is not like one of these, but is orange one. Okay. Yeah. So this is the equation. What does the equation look like? And how to find the components in this equation? How to find the slope and the y-intercept, and the theory behind this method. Okay. And in my next video, I will show you a easy way, a quick way to find this equation without finding these components one by one. Okay, but on the quiz, you might see questions like this. Of course, I will give you these components and ask you to use them to find the B1 and B0. Sorry, this is supposed to be B0. Yeah. Okay. Yeah. I will see you in the next video. Okay, bye.